Hello everyone, this is my ELP 101 project and I am Swapnil Kashyap. My topic is detailed analysis on instrumentation amplifier. So what is an instrumentation amplifier and why do we need it? The input to an instrumentation amplifier is the output signal from the transducer. A transducer is a device which converts one form of energy into another. Most of the transducer outputs are of very low level signals. Hence before the next stage it is necessary to amplify the level of the signal, rejecting noise and the interference. Many industrial and consumer applications require the measurement and control of physical conditions. These changes in physical conditions must be converted to electrical quantities using transducers and then amplified. Such amplifiers, which are used to amplify signals to measure physical quantities, are commonly known as instrumentation amplifiers. So what are the requirements of a good instrumentation amplifier? Finite Since the instrumentation amplifiers are required to amplify very low level signals from the transducer device, high and finite gain is the basic requirement. The gain also needs to be accurate and the closed loop gain must be stable. Easier gain adjustment. Apart from a finite and stable gain, variation in the gain factor over a prescribed range of values is also necessary. The gain adjustment must be easier and precise. High input impedance. To avoid the loading of input sources, the input impedance of the instrumentation amplifier must be very high, ideally infinite. Low output impedance. The output impedance of a good instrumentation amplifier must be very low, ideally zero, to avoid loading effect on the immediate next stage. High CMRR. The output from the transducer usually contains common mode signals when transmitted over long wires. A good instrumentation amplifier must amplify only the differential input, completely rejecting common mode inputs. Thus, the CMRR of the instrumentation amplifier must be ideally infinite. High slew rate. The slew rate of the instrumentation amplifier must be as high as possible to provide maximum undistorted output voltage swing. So this is the internal circuit of an instrumentation amplifier. We can see three op amps being used, and this R1, R gain, R1, R2, R3, and this is also R3. So I'm marking this terminal as E, G, H, and F. The voltage at E being VO1, the voltage at F being VO2. Now the potential at node A is the input voltage V1. Hence the potential at node B is also V1 from the virtual short concept. Thus the potential at node G is also V1. The potential at node D is the input voltage V2. Hence the potential at node C is also V2 from the virtual short. Thus the potential at node H is also V2. Ideally the current to the input stage op amps is 0. Therefore the current through the resistors R1, R gain and R1 remains the same. Between the nodes E and F, we get I equal to VO1 minus VO2 divided by R1 plus R gain plus R1 from we can write this as I equal to VO1 minus VO2 divided by 2R1 plus R gain. Since no current is flowing to the input of the op amps 1 and 2, the current I between the nodes G and H can be given as I equal to VG minus VS divided by R gain, that is V1 minus V2 divided by R gain. Equating equations 1 and 2, we get VO1 minus VO2 divided by 2R1 plus R gain equal to V1 minus V2 divided by R gain, that is VO1 minus VO2 is equal to 2R1 plus R gain into V1 minus V2 divided by R gain. The output of the difference amplifier is given as Vout is equal to R3 by R2 VO1 minus VO2. Therefore, VO1 minus VO2 is equal to R2 by R3 Vout. Substituting VO1 minus VO2 value in the equation 3, we get R2 divided by R equal to 2R1 plus R gain into V1 minus R gain. That is, Vout is equal to R3 into 2R1 plus R gain divided by R gain into V1 minus V2. The above equation gives the voltage of an instrumentation amplifier. The overall gain of the amplifier is given by the term R3 divided by R2 into 2R1 plus R gain divided by R gain. So some key points to note here. The first one being the overall voltage gain of an amplifier can be controlled by adjusting the value of resistor R gain. Now also the common mode signal attenuation for the instrumentation amplifier is provided by the difference amplifier. So what are the advantage of using three-phase op-amp instrumentation amplifier? The gain of three op-amp instrumentation amplifier can be easily varied and controlled by adjusting the value of R gain without changing the circuit structure. The gain of the amplifier depends only on the external resistors used. Hence, it is easy to set the gain accurately using the values carefully. The input impedance of the instrumentation amplifier is dependent on the non-inverting amplifier circuits in the input stage. The input impedance of a non-inverting amplifier is very high. The output impedance of the instrumentation amplifier is the output impedance of the difference amplifier, which is very low. The CMRR of the op-amp 3 the CMRR of the op-amp 3 is very high, and almost all of the common mode signal will be rejected. So what are its applications? It can it is also used as a light intensity meter, and it is also used as a temperature indicator. So some concluding remarks. So in this project, we commenced with some basic concepts of instrumentation amplifier and discussed about its need. Then looked at the specifications of a good instrumentation amplifier. Then we dug deep into its internal circuit and did some math to voltages. At last, we get an idea about the applications of instrumentation amplifiers and saw its everyday usage. Thank you.